Well, I'll assume that this is everybody and people come in a bit late. Welcome back for the afternoon session. Just a last reminder that the next presentation after this one is the change to the program. But in the meantime, we've got Lars from SimCorp, who's going to talk to us about Sparse Data.
Good afternoon. This is kind of like a challenge because having all these knowledgeable APL people in the room, it's always hard to do a presentation that actually involves code. Although I still want you to interrupt me if you find something that you think is not clear or precise in what I'm doing. I have this agenda that I hope will make in 45 minutes. I have to talk about my company. This is marketing doing these presentations, so we have to talk about it. Then I'll try to motivate why on earth I'm talking about sparse matrices, sparse data in general, and then I'll try to give a definition. Then I'll show you 3 different data representations of sparse matrices. There is a number of them out there. These are just the 3. 2 of them is quite obvious, and the third one is one we've used in real-life example because we had a real-life issue. Then I will try to implement some operations on these structures. And then this famous word, institutionalize. Institutionalize is a word that SimCorp learned from a model called CMM. And it simply means get the stuff out so your developers is using it and how you should do that. And this is actually, I think this is... It's a one slide in my presentation, but it is by far the most important one here. So hopefully that will do. Okay, SimCorp, we do investment management systems. We've existed since '71. We're 160 APL developers. We are 70 C# developers, and we are 400 people in total in the development division of SimCorp. So we're pretty big. And we're just like Eleanor talked about, when you grow to a certain size, you have to have control over things. And this is also partly what this presentation is about. A bit about motivation. SimCorp is using a 64-bit version of the Dyalog. That should be enough, right? Well, we often work in environments where a number of people share the same machine. So we can just not give them 2 to the power of 64 bytes of memory each. That will simply not work. So that's one of the reasons why we're doing this. Another thing is that we kind of like everywhere in our application, we think of the data as being records, and the columns represents the different attributes of these records. In a normalized database version system, you wouldn't have a lot of zeros, but it's more convenient for you to have kind of like all the attributes represented in records, because then they're there when you need them. That means also that a lot of these values are not represented, so they're 0. Our data is homogeneous, meaning that's exactly what I've just said. Each property represents the same kind of data all the way down to a matrix. And then this is actually a real example. 4,000, where we were talking about indexes during lunch. There is a North American index having 4,000 position in it, meaning securities. We had a customer that had 3,000 clients that they are administrating in the system. And they were trying to do allocation of these indexes using an LP algorithm. So we ended up with a matrix of the size of 4,500 and 12 million. We couldn't solve that, I have to admit that. But we ended up solving about 1/20th of this problem in 200 megabytes of workspace. Sparse matrix definitions, well, I've just briefly mentioned it. Go to this Wikipedia article and look for it. It's very good. As I said, there is numbers of ways you can represent sparse data, and I've just elected 3 of them. But anyway, sparse data is by nature easily compressed, and this compression always results in significant computer data storage. This is kind of like less data storage. This is kind of like the red line in my presentation as well. We have to save space. Okay. A lot of zeros, a lot of repeated values. I didn't know that John was going to talk about Sudokus. Gita is talking about Sudokus as well. Everybody's talking about Sudokus. But anyway, as sparse data, Sudokus, even though it's a small example, this is my example all the way through the presentation. It's not big, I'm sorry about that. And if you get bored, you can try to solve it without cheating and using John's algorithm. But it represents a sparse matrix. This has a density of 43%. That means 43% of the values are filled out. And the harder this Sudoku gets, the more sparse it gets. Okay, that's one example. Another example, which might not be quite as obvious, is this is our partner table in our development system. I'm querying that for an internal key, the name of the partner, and free code 41, which by coincidence is named free code 61 in our user interface. I'm giving this presentation in-house as well, and I like to blame people for naming something 41 and then showing it as 61. That's a different story. We have 14,000 partners and three columns in this. The unique key is unique, right? So there's 14,000 different values. The partners have unique names, yes, but there's just one free code. This is also sparse data. And coincidentally, the value is 0. Okay, just for all these quad IO 0 people and ML different from 0 people, this is what we work in. This is kind of like hard-coded and everything in my application. You have to do your transformation yourself if you want to do different values. Okay, this is my Sudoku. This and this. They're alike, right? Okay, Ken, my good colleague that's sitting here in the back, he often uses this definition. I think he stole it somewhere from Dyalog, or did you invent it yourself? Yeah, well, okay. We have a matrix here that's 128 bytes. If we multiply the dimensions by 100, just so the upper left corner now is the only place where it's actually values now, and then we have 99 times 100 zeros into it, it grows to almost a gig, right? It's 100 times 100 times 81 plus 40. So this should actually be 121, but I guess that's rounding to words. Isn't that correct, Griff? Okay, so we have a matrix here that's about a gig, and then we're implementing the first data structure here, which is a list of lists. Every time you talk to experienced build programmers, they say, well, you should never mix data. So this is the list of lists. Here is actually making each column in your matrix a list. Nothing else, right? So a big matrix was like 810. And now I've made this lol, list of list. It has 151.88. So the only thing I did was I made a list of lists. I have exact same data represented as I had originally. I've not cheated, I've not done anything. And the reason why this happens is because Dyalog has a very, very, very efficient way of representing Booleans. So the first 15 values here should represent, well, only the first 9 columns, because I've filled the rest with zeros, is small integers, 8-byte integers, and the remaining is 1-bit bytes. So just by doing this, I know this is not a real-life example, but it gives you kind of like an idea what kind of compression you can obtain just by doing what Dyalog does. Okay, and I've made a small constructor for my list of lists, because I'm going to need that. It's a defun, very unusual for me. Very, very simple. Okay, I didn't show the size of the list of the the small matrix, the 128, because that's kind of discouraging. So instead, I'll say, okay, let's try to do something different, right? So now I want to try to solve this Sudoku. I think I'm not quite sure. So what I do is now, instead of having a scalar value of 0, now I put a vector of 4 in here, because I'm not sure I need a way to represent that this is a guess, right? Okay, what happened? It went from 128 to 3,288 bytes. Okay, I'm going to make a list of lists on these. 888. Now, we're talking about a structure of 9 times 9. And you see me save almost down to a quarter of the size of this internal structure. I know, Jeff, that there is sometimes that the size will not give the correct answer and the value will be repeated, but bear with me for making this for simplified assumption here. And it is actually the exact same issue that we saw when we were adding zeros to the columns here. That now the only one that's kind of like difficult is the first column now, because this is one here. It has to be a nested structure of pointers, 6 pointers of 32 bits, then 8 points to 9 different values, and this is kind of like taking a lot of space, and the rest here is taking, 128. So if you're mixing that, this is 101 when we have new APL programmers coming in here, and then they say, oh, okay, we got to put tilde in here because we don't know what value to take, and everything explodes in their head. So it's actually nothing to do with Sparse Matrix, but it's kind of like different. Okay, the next representation is, it's called a coordinated list, abbreviated COO. And when we had this problem around Christmas time, I called Morten, and I said, Morten, I have a problem. I can't solve this. We're running in workspace full. And then he said, well, have you tried this one? The idea is that you save the indexes of the values different from 0. This is this expression up here. And then you save the values. Any of you got an idea why you want to separate those two? Coming in, Ray? Exactly. What Ray says is that these posts would have a maximum value of n or m, depending on its rows and columns, whereas this could actually be floating points or pointers to text or whatever. So you want to separate those two. Okay, yeah. So I'll do a COO where I remember the shape of the original matrix and my posts and my vals. Why do I need the shape? Well, I need it because if I add 15 rows of zeros and 15 colors from zeros at the end, I wouldn't know the original dimension of the matrix. So I need that. This will give me a size of 280. This is not as bad as the previous ones, and I'll show you. And compare that with a matrix of 128. I'll make a dynamic function more, very impressive, for doing this construction up here. And I'll do this not on a 10 times matrix, but just a matrix that's 4 times as big. So I've added 9 columns and I've added 9 rows. Okay, I'll do a coordinated list on this, 280, the exact same size. Wow. I multiplied the size of the matrix by 4 and nothing happened. Whereas this is actually represented here, that the big matrix is now sufficiently larger. So remember I talked about the 43%. This is the density of the original matrix. And the density of the big matrix, the 4 times, is 11%. Kind of like this divided by 4, I think. So in the case where you have 11% values different from 0, this makes sense. from a space point of view. Okay, this is another industry standard, and I'll try to explain this the other way around. So I'll give you the idea of how to present this. This is called a compressed sparse row. It has a cousin called compressed sparse column, but you can look that up. It's an industry standard, and the reason why we chose to use this one, this is the one we used for our algorithm in solving this problem with the huge number of rows, was that this is very, very efficient for doing matrix multiplication, especially when you're using Dyalog APL. I hope I will be able to kind of like illustrate that. Well, anyway, the idea is that you save the values in an increasing. So you say 6, 7, 5, 4. So illustrated by the red lines here. The next thing you do is that you save the column positions. So this is 1, 4, 6. I didn't write that one. 4, 3, right? You get this? And then row start. And this is the hard one, because it takes you a very long time to get around this. But this says, where does the value for the first row start? Well, they start in position 1. Where does the row values of row 1 end? Well, in 4 minus 1. So 1, 4, and 6 belongs, the value 6, 7, 5 belongs to the first row, being in position 1, 4, and 6. So row 1 is found by this, 2, this minus this, plus minus the index. And in general, you can write this as how you find the rows. Okay, so how do you find this? The values is just like before. The positions is kind of like a little more. By the way, I haven't written this anywhere, but as part of my presentation upload to Andy, I've also given you a workspace of these very, very simple functions, and you're more than welcome to come back to me if you want to have the more complicated ones we've written. Okay, so finding the position, and then how do you find the row start? Okay, then there's some identity values here that you always have one more value in this than there's rows in your original matrix. Stated up there, and some identity. This is again, this is the structure, data structure we're elected to represent this in, and we see that this is giving us a CSR of 296. The constructor for this, again, our 4 times larger matrix. Now 304 again. So this is not as efficient. If you may recall it before, it was like 8 bytes lower before. But it's not as efficient as the COO from a space consumption point of view, but it is far more efficient when you're actually manipulating these. Okay. Well, there's no reason for having these structures unless you can actually get data out of it again. I mean, it's not a write-only operation, so you have to kind of like implement these different ones. So this list of lists, the one I originally suggested, if you want to have the columns 1, 2, 3, and the rows 1, 2, 3, 1, 2, 3, 1, 2, 3, you get this. You can implement it like it. I think it's right. I hope it's right. For CEO, I'm not sure this is the most efficient one. This is one I invented just for my presentation. There's probably much better ways of doing this. Morten has something with encode you can use instead. I haven't implemented it here. And the CSI is slightly more complicated. Okay. So far, so good? Okay. Is this for free? By no means, no. It is. This is extremely expensive. Right. If you take your ordinary row column indexing and compare that with all of these, you see actually that the CSR is, much slower in this case. So why on earth do you want to do this, Lars? Well, first of all, an algorithm that is VS full prone, well, that's not an algorithm, right? It doesn't work. We were when we implemented this, we asked our businesses, said, well, what are the time limits we're giving for this? Well, you should solve this factor of 20 problem in 1 hour. Okay. And then that was a tough benchmark to go up against. And then the first solution we made was 1.5 hours, I think. And then we said, well, on the other hand, we've never seen this solution before, right? Because it was VS full. I have to add to this that the reason why we were particularly hit hard by VS full was this was running in the 32-bit version of the APL, because, things are a little better now. And this is not entirely true, that it is slower. These gets are slower, right? But this is a test function. I shouldn't say test if Kai is in the room, because it has nothing to do with test. But this is a simple function where I compare a traditional APL product here. I don't know if you can see that one, but that is a traditional product, and I compare it with our CSR math, compressed by row matrix product right here. I had to have a huge matrix to see the kind of like the interesting results in this, but we now have a matrix with 1,800 columns and 1,800 rows. The size of the matrix is 3.2 gigs. Big. Kind of like forgot which one. My algorithm, or our algorithm, is doing this in one cycle, where it's 1,500 milliseconds. The matrix multiplication in the APL is taking a half a second. And I'll just briefly show you this. This is the matrix multiplication in the CSR wrote, and this is the key. Trust me, it is the key. That is actually that you can use the plus assignment, where you have repeating values in your keys here. This is actually why this is working so good in APL. A lot of our more experienced APL programmers say we're not allowed to do this, but you should know what you're doing. But in this particular case, it actually solved it. Another, I think it's a quite funny story. I found this algorithm on the internet, and it was a C implementation, so it had 2 loops. So what did I do? Well, I'm a Dewey. I'm sorry, I am a Dewey. So I wrote those 2 loops, and it performed like shit. And then I looked at the code, and Ken can confirm this. And every time he came to my desk, I had found a way to eliminate some code. So having this huge loop construction, maybe I can find it, but it ended up being like, this is just APL, right? Another interesting fact about this, first of all, you have to verify that it is actually giving the same result. So I've taken the top left corner, and you see it does give the same, i.e., it works. Look at the size of this, 26K, right? Compared with this, right? And more interesting fact is that the result of the APL matrix multiplication has actually doubled in size. So we have 26Ks compared to 6.5 megs. And that's the reason why it's so much faster here, because we have to work on much less memory. Okay? And actually, just for Kai's sake, I have actually verified that they are identical, those two. Okay. I'm almost at the end of this talk and demo, kind of like PowerPoint presentation stuff. let's talk a little about institutionalization. Well, if you're a single programmer, I think you can live with doing this, right? You take your list of lists structure and you call your get and your R and C, and then you get the values out. But do we really want to do that? I mean, there's a lot of talk about domain programmers, and one of the kind of like agreed on rules for us is that we work on matrices where each column represents the different properties of the matrix. So we want to have a matrix, right? We want to do like this. Because otherwise it doesn't make sense. And, I mean, this is something that I've actually been working on this precise issue of having something that is a compound structure represented in a more natural APL stylish way of doing things. So if you do this with the class encapsulation that Dyalog has invented here, then this will actually bring you quite a long way. I'll give you the example here. And this is, by the way, this is not in the documentation. No, I have reported it to Vince. So John made it for me. But anyway, the reason why I did, but that's another story. This is something I stole from Paul Masur. So sorry he's not here. This is kind of like a static method. For instead of writing quote new to objects, we like to say object.new. There we give the data and the matrix in here, and then we put it down. This is a list of list matrix, right? And then this key default values where you can make a get. I haven't implemented a set, but you can do that yourself. And then you can say whether or not you've actually specified the first part of the index, or the key, or the second part of the key. And then you can refine my get code here, the one that I showed you before. And then it just works. lol matrix, right? lol iota 3, iota 3. I think I can't stress enough how important I feel that this feature is, because now this is a list of lists, right? But I haven't chosen any kind of matrix implementation inside this. I could have shielded away from everybody else but me owning this object. I would give them the penalty of performance maybe, but at least I'll give the benefit of space saving just by having this. And they can continue to use it. I know they can't continue to use it because if they say lol comma, a vector of, you would get some strange results. But that they have to learn that. But all the rest of the way they can actually use this. Does this make sense? Okay. Are we on time? Maybe I should take some questions. And I have a demo of some more sophisticated, if you will, sparse implementations we've made in-house. But I'd like to hear what you think. Any of you? Yes?
It was not a problem for you. I've been playing with something similar a few months ago, and at the beginning I was really excited about the possibility to use a class to look like a matrix which internally was stored in a completely different way. But this stuff is a class. For some strange reason I never really understood, its value is not a value but a reference. So in a lot of constructs, this is not working. Don't you think that it would be nice to have an APL class object which, as a value, if I just write the name as in APL, will give you the value, so you can do normal activity on it?
What, if I'm understanding you correctly, Carlos, you're saying that all the traditional, I can't do transpose on this, right? This, for example, right? And what you really want to have is then, okay, do I really want to override transpose?
This stuff is not an APL object. It's something alien which somehow works as an APL object in something. If you do indexing and assign something to some sub part of it, it works. But on any other point of view, is different. It's not a matrix. You can index it only with brackets, if I remember.
You're probably right, but that's what our developers do.
You cannot ask the shape. No. We have a lot of code which is doing row of something, and this should be changed. So the ability to mimic the original APL object is somehow limited by this stuff whose value is a reference, which is not something of APL, it's something alien coming from a different world.
Well, I agree a long way with you, Conrad, that what we probably need, as a minimum, we need a way to implement those functionalities that we will use in this. And I have briefly discussed this with Morten as well. Another way of thinking about this is let Dyalog do the work. Right. I mean, why on earth? I mean, you saw my compressed sparse road product and all these. It's a lot of fun, and from an intellectual point of view, it's very fun to do. But on the other hand, find some way of thresholding these 43%, 11%, and then Dyalog, let do the magic. And I know we're quite a long way from that, but I mean, if we do a presentation like this again in a couple of years, maybe we can persuade them that this is actually something. Jim is nodding. Very good. Yeah. Roger?
Lars, what's the typical density of the matrices that you deal with? And the second question is, what's the largest matrix multiplication you have done so far, whatever the density?
Let's talk about the density first. This was a linear programming problem. So if you're familiar with that, it was the A matrix in the condition. And normally a linear programming problem would have 3 values in each column different from 0. And that's kind of like, it is, and I think maybe Ken can help me here, but I think we were around 130,000 rows and 4,000 columns. Yeah. Did you get that? 135,000 rows and 4,000 columns.
Yeah, I mean, maybe I should say something in response to Carlo's comment. I mean, this is certainly an issue we are aware of, and we do have sort of very sketchy plans on the drawing board. It's a question of prioritization. We could certainly implement a type of class which was, I guess, a value type rather than a reference type, where the object would behave as a matrix completely, and where you had the opportunity of somehow declaring which operations you wanted to implement in your own APL code. So plus.times, I guess, you would want to implement yourself, but you could allow other operations to default to the APL behavior.
Right.
Have you thought about using operators, a sparse operator?
No.
I did some work some time ago with that, and that seemed to be quite useful.
From what perspective? From the readability, or
you could by using a sparse operator, you could change how you compressed your data, but you were also able to write. You just needed to, when you had a function, you just needed to put the sparse operator between your function and your data, and you're doing a plus, and so the operator deals with the sparseness.
Okay, yeah, I see. No, it sounds like an interesting way of going. Maybe I should go a little bit out of line and then try to show some real code. This is something that always goes wrong for me. if you remember, I had this partner data stuff going on here. So I have this sparse example. You can recognize the query I've done here. Get the rows, get the size, and then this is a totally different implementation I have here. This is one that compresses data, because this is one where we actually try to see if we can use repeating values and all this. And I'll gladly share this one as well with you. It's not in your package. You can see here I've implemented the Sparse Matrix, get me the first 10 rows. When I execute this one, you see that this fairly aggressive compression brings me down from 1.8 megahertz to just under a megahertz. And remember, there was only one repeating column in here, right? Still unique values. But first of all, the 0 is stored as a 0 in the internal one. And the index, it had to share 32 pointers for everything else in the PD, because it is a mix of integers, text, and booleans. So this example actually shows that even on data that has nothing to do with linear programming, you can obtain quite dramatic space reductions. I don't want to do any more coding, so... Any other questions? Good. Thank you, then.
Thank you.